All right, good afternoon and welcome to our last webinar Wednesday of the year. Today's topic is the promise and possibility of heat transfer 100% outside air underfloor-radiant systems. And Dan Hahne is our presenter. I'll leave this up here for a second, let you guys all scan that QR code if you want. Shameless plug to follow us on all of our socials. It will take you to our link tree that has a lot of information there. My name is Kelly Huff. I am the marketing manager and Dan's partner in crime for our educational platform. Next slide. And we are Varitec, the HVAC system solution provider. We cover multiple disciplines, and we are shaping the future of HVAC. Our mission for our educational platform is to continue to provide an educational platform for continued learning in the HVAC industry. We focus on high performance buildings and innovative technologies for a better built environment. So right now, Dan and I are hard at work coming up with a schedule for 2025. It's a work in progress, but we will be back in February, so keep an eye out for what the schedule will look like next year. And Dan does have a lot of presentations already put together that are AIA accredited. So if you do need a presentation between now and February or anytime, you can always reach out to him and get one scheduled directly at your office. We also have our newsletter. It went out this morning, so hopefully you guys saw it. If you didn't, let me know and I can get you added to our mailing list. As you saw at the beginning of this, I hit record. I put all of our recordings on our website under our resource library. Once this presentation is over, that's where it will go. And we have a lot of upcoming events and educational opportunities. We actually just finished the Albuquerque Roadshow yesterday. I was there. It was cold. Thank you for everybody who came out and stuck with us through the cold. This Friday, we're in El Paso. That's where I am right now for the Fiesta Roadshow, where we have a bunch of different manufacturers that will be there, and it's going to be a great time. So if you're in El Paso, you should definitely stop by, and then look for it coming to Arizona in January. As I mentioned, Dan is our professor for the day. He has a great history in our industry, a lot of experience, almost 40 years with various rep firms around the valley. He has been with Varitec since 2016, and he is our director of high performance HVAC solutions and our educator. He is an ASHRAE member, and he is very active in ASHRAE. He is on the standard 200 2015 methods for testing chilled beams. He's a voting member. He is also on the TC 1.7P, the Ongoing Building Commissioning Committee. He's a voting member there. And he is also a distinguished lecturer. He also has a lot of publications in ES Systems Magazine, and I believe there might be one coming soon. So stay tuned. And with that, Dan,
thank you.
I will pass it over to you.
Thank you, Kelly, and thank all of you for joining us today for our last edition in 2024 of Varitec's Webinar Wednesday. My name is Dan Hahne, and today we're going to sort of step out and do something a little differently today. We're going to look at the promise and possibility of heat transfer, 100% outside air, underfloor radiant systems. We're going to look at a number of previous presentations and try to bring them together to demonstrate how, with a little creative thinking and application of the laws of physics with certified equipment, we can actually improve efficiency on HVAC systems, any MEP systems, as well as create healthier, better built environments. Today we're going to look at the promise and possibility of heat transfer. We're going to look at a conventional mixed air system. Then we're going to look at modes of heat transfer. We're going to look at mechanical modes of heat transfer and passive modes. We're going to look at 100% outside air systems and the value they offer to building design. We're going to look at underfloor air systems and passive radiant cooling and heating systems. And then how, if you blend them together, it offers a very compelling design solution to meet ASHRAE's and our nation's decarbonization initiatives while creating healthier buildings. First of all, before we begin, on behalf of Varitec's Technical Institute team, thank you. Thank you for joining us throughout this year and participating in our program. We hope is giving you information that is relevant and that you might be able to apply and consider in the future. Today, however, we're going to connect the dots, as mentioned earlier, and bring a couple of system concepts together that I've presented to independently through previous sessions. So let's look at the promise and possibility of heat transfer, and let's look at a common conventional mixed air VAV system, a system still widely applied today, certainly for medium and large sized buildings. Again, let's look at why we do HVAC. Well, it's to create indoor environments that are conducive to well-being by maintaining thermal comfort and good indoor air quality. And since the pandemic, ASHRAE has now adopted a standard 241 with strategies in order to reduce the risk of infection within the built environment. And it states within the standard 241's initial statements that some of these recommendations will gradually be adopted into 62.1. So stay tuned for that. Well, the purpose of HVAC systems, again, is to promote thermal comfort while maintaining good indoor air quality. And to maintain good indoor air, good thermal comfort, we have to move energy. That's the whole purpose of an MEP system, is to move energy. In cooling, we move energy that builds up from inside a building and deposit it outdoors to maintain space set point temperatures at thermostats. And in heating, we add energy that is lost to the outdoor cold environment where thermal energy tries to escape to a colder area because due to the forces of thermal equilibrium. So what is energy? Energy in physics is the capacity for doing work. There are many types of thermal energy. Specifically today, we're going to discuss thermal energy and electrical energy. So in a conventional mixed air system, in order to move energy, what we first of all, our first goal and objective is to create, per ASHRAE guidelines, a unified thermal condition throughout the cubic volume of space within plus or minus 2 degrees. And to achieve that, we injected high velocity 55-degree air through diffusers. And that high velocity air creates a negative pressure zone that induces room air into the supply air jet, allowing for mixing to occur. Well, the question is do well mixed room conditions actually occur? Well, they can at peak load. But what about VAV systems at part load? At part load, variable air volume box is throttled back, airflow is reduced, discharge velocity at diffusers is reduced, and consequently, the proper thorough mixing in a space is compromised. So having a fully mixed air environment during our part load conditions is a challenge due to the negative buoyancy effect of cool air coming out of the diffusers, dumping into the building, failing to induce room air into the jet for proper mixing. So another thing to keep in mind with a mixed air system is that air is the heat transfer medium in the space. The problem with air is it's not a very dense heat transfer medium. It only carries 0.46 BTUs per pound of air. However, to adopt a more energy efficient design strategy, what if you used a more dense heat transfer medium, such as water? And many engineers of large institutional facilities have realized that by designing central plants and chill water systems to large educational structures or hospitals or whatever, because water is more efficient in moving that energy from the building to outdoors than a lot of packaged DX rooftop units on a roof. But again, another factor, what about refrigerant as a heat transfer medium? And I've spoken to this in the past. What if we actually bring refrigerant into a building, into each zone, and allow it to be the heat transfer medium? We find that by using water or refrigerant and bringing water or refrigerant local to each zone, we can actually create more efficient systems by the reduced pumping horsepower compared to the fan horsepower otherwise required, and also the vapor compression cycle in variable refrigerant flow systems. So, the promise and possibility of heat transfer. How can we look outside of the mixed air solution for conditioning our buildings to maintain thermal comfort and humidity levels within a space? First of all, what is heat transfer? A reminder, because I've shown this slide before. Heat transfer, according to Britannica, is any or all of several types of phenomena that convey energy and entropy from one location to another. There are two forms of heat transfer. There's mechanical heat transfer that uses electrical energy in the form of kW, kilowatts, in order to move thermal energy or sensible heat energy to or from a building. So energy is consumed in order to create the heat transfer from a building. There's another form of heat transfer. It is passive heat transfer that relies on the natural force of equilibrium in physics. Wherever there is a energy present at a high energy state, it spontaneously moves to a region of lower energy. It automatically happens, such as radiation from the sun. So there are four types of heat transfer in the realms of physics. There are only four, no more, no less. There's conduction, evaporation, convection, and radiation. Conventional all air or mixed air HVAC systems use mechanically forced heat transfer modes. Conduction, where air that is being conditioned is in direct contact with the fins of cooling or heating coils. And then evaporation, actually it's evaporation condensation that we see in vapor compression cycles in chillers, where heat transfer is controlled by pressure control within the vapor compression cycle. But it's an evaporation condensation of refrigerant that allows for that transfer of energy. We also see it in packaged DX equipment on roof. DX equipment uses the principle of evaporation and condensation in order to move energy from the building to outdoors. So what are the passive modes of heat transfer? Convection, motion caused by hot, less dense fluid to rise and cold, more dense fluid to fall. In other words, hot air rises, cold air falls, is the force of convection. It's driven by thermal buoyancy factors. Warm air is less dense than cool air. Another passive mode of heat transfer is radiation. Heat transfer to the emission or transmission of energy in the form of electromagnetic rays. What is the biggest source of heat transfer on Earth? Well, it's the sun, as we all recognize. That is radiant energy that does not heat the air, it heats surfaces. Radiation occurs between high energy states of one surface transmitted or emitted to another surface of a lower energy state. So in high performance HVAC systems, one of the reasons why these systems offer the promise of their efficiency is that not only two modes of heat transfer are applied, mechanically, conduction and evaporation, but also the two passive modes of heat transfer can be applied, convection and radiation. So the promise and possibility of heat transfer. We're pretty aware of the mechanically driven heat transfer modes of conduction and evaporation. What about the passive modes in a HVAC design, convection and radiation? Well, first of all, passive heat transfer can occur by creating thermally stratified environments in a building or in a space. instead of maintaining a mixed air uniform temperature throughout the cubic volume of space of plus or minus 2 degrees, we actually let the space be stratified. The temperature at the floor will probably be at about 70 degrees. A thermostat at the thermostat set point of 75 degrees. And then we want a warmer air region in the upper levels of the space at between 78 to 82 degrees. It can be more depending on how tall the ceiling is. What is the space sensible load? There are a lot of different factors depending on the application. So how do you create a thermally stratified environment? You use displacement ventilation, a topic that I've been speaking to, now for over 15 years, and we've had many successful installations. How does displacement ventilation work? You actually inject air at low velocity, not 150 feet per minute, but at 40 feet per minute. The air supplied is of a warmer temperature, not 55 degrees, but 62 and 68 degrees. And the upper level of a space could be anywhere from 80 to 85 or 78 to 82, as mentioned previously. And then that air, that warm contaminated air in the space, is exhausted from the room through return air grills that brings air back to the air handler or exhausted from the space. So to give you a look at how convection works in a thermally stratified environment, I'm going to show you a video, hopefully it all works, provided by Kruger, our manufacturer for air distribution products. And you can see, excuse me, sorry for the music, it is a little abrasive. If you look at the two displacement diffusers on the opposite side of the room, you can see air is brought into the space at low velocity, and on the opposite side of the space, well, it's hard to talk through that.
Is that coming from your computer, Dan?
It's coming from the video, Kelly.
Oh, okay. Okay, cool.
There, I just muted it. There we go. All right, sorry about that. If you notice, there's a heating device on the opposite side of the room. But because that device is warmer than the room temperature, it gives off warm air. Warm air rises, cold air falls. And when it does that, it induces the cool air provided by the displacement diffusers into that thermal plume emitted from the heated surface, allowing that warmer contaminated air to rise to the upper levels of a room. So it's a very effective process, and ASHRAE recognizes its effectiveness by assigning it a higher ventilation effectiveness value than conventional HVAC systems. All right, I apologize here. Why isn't it not advancing? There we go. All right, so displacement ventilation. What is the indoor air quality advantage? Well, ASHRAE standard 62.1 as I just mentioned, assigns it a 1.2 ventilation effectiveness value and allows for a single piston of clean conditioned air to cross the breathing zone of occupants. Again, all of the contaminated warm air is drawn to the upper levels of the space where it's exhausted through grills in the ceiling or in the upper level of the walls. Well, underfloor air systems also offer the promise of thermally stratified environment. They can be designed to provide displacement ventilation to a space and to create a thermally stratified environment. The difference here is that instead of using low in-wall diffusers, a pressurized plenum floor is used with diffusers mounted into it, and air from that plenum at low pressure at 0.05 to 0.08 inches injects air into the space to allow for that thermally stratified environment to be created. So at these lower pressures, underfloor air systems offer an added level of efficiency to displacement ventilation. Also these systems, because they supply warmer air, as mentioned earlier, at 65 degrees, there's another level of efficiency added by doubling economizer hours, certainly in our Sonoran desert climate. So There's another energy efficiency advantage to underfloor displacement ventilation. So, is underfloor effective in creating healthier environments? Well, according to a Nature Scientific Reports publication in 2022, it showed that implementing upward ventilation is the most effective measure, followed by wearing masks to reduce the risk of infection. In fact, it says that it can reduce the indoor infectious concentration by nearly 99.95%, compared to a mixed air system, which is doing its job if contaminants in that space are being well mixed. And there's some arguments that are out there in the market today that are challenging our concept of how contaminants actually travel back to an air handler. Do the smaller submicron particles actually make it back to the air handler to be properly filtered? So another passive mode of heat transfer is to use radiation by creating a thermal imbalance in surfaces of a space. If we cool or warm surfaces in a space, let radiation do the heat transfer work for you. By cooling a ceiling, then any surface that has a higher temperature or energy level than the room set point condition will emit its radiant energy to the cooler surface. It occurs spontaneously and at the speed of light. So by using passive modes of heat transfer, we're allowing the laws of physics to go to work for us, as opposed to using mechanically driven systems that consume energy to move energy. To enhance that heat transfer capability with a radiant heat transfer system, you want to use a thermally stratified environment. You want to make sure that you increase the delta T at the radiant device adequately, so that in the cooling mode, it can actually have maximum heat energy transferred to the water side of that mechanical system, because water is a more dense heat transfer medium, and that sensible heat energy that is absorbed at that radiant device can be more efficiently removed from a building using pump energy than the otherwise added horsepower energy that would be required for mixed air handler fans. So in passive radiant systems, thermal stratification is required to optimize the performance of a radiant system. Well, let's look at another system that I've spoken to in the past, 100% outside air systems. What is a 100% outside air system? What is the objective? The objective is to decouple the outside air component from the conventional MEP system. We want to decouple it. We don't want to put an outside air intake into an air handler and allow that outside air to mix with the return air. We're going to condition that outside air independently of the mechanical system. So it's designed in parallel too. The advantage of doing that is that we can apply heat recovery strategies that can easily result in a reduction of 25% of the outside air load, depending on whether or not you're using sensible heat recovery or enthalpy heat recovery. And there are different ways, different technologies available today on that heat transfer solution, and it's continuing to mature and develop. There's some pretty compelling technology available today with some of our manufacturers. So by using a 100% outside air system, we do want to make sure that the relationship between the outside air supply flow rate is a little greater than the exhaust air rate, so a building's pressure is always positive to the outdoors, because if you have negative pressure in a building, you'll suck in either very cold air at our coldest times of year or very warm, hot air at our various high time of year. So in looking at DOAS units, we want to have the right balance between outside air versus exhaust air. So a couple of advantages outside of reduced outside air load on a MEP system is you can now inject in a 100% outside air system the assigned outside air rate to each zone, because it's always been a challenge in ASHRAE to assume that because we have a mixed air plenum and an air handler, we're getting the appropriate distribution of outside air percentage to the return air percentage distributed uniformly throughout each zone within a building. How do you verify that? Well, it's very difficult, if not impossible, to do. So 100% outside air system allows you to inject that outside air directly to each zone. It can also help control the concentration of CO2 levels that ASHRAE is evaluating today, in fact. There are papers out there suggesting that CO2 levels should be limited to not to exceed 1,000 parts per million, and there are even some reports in the ASHRAE journal that maybe the target should be 600 to 800 parts per million. The only way to control CO2 today without some pretty compelling new technology that's just beginning to get into the industry is to provide more outside air to your building. Outside air has lower CO2 levels than the indoor environment, even in LA, which has a staggering 700 parts per million plus in its outdoor air on a January, February winter's day. There are schools being measured in the country at 1,500 parts per million, offices at 1,500 parts per million. Schools, in fact, have been registered to read at over 2,000, 3,000 parts per million of CO2. An environment where we want our students to be alert and awake, and now we're overwhelming them with higher levels of CO2. It's going to be a challenge. So the challenge with 100% outside air systems, though, is that the outside air supplied to a building has to be properly conditioned to a low enough dew point to assume the role of humidity control in the building. It has to be dry enough to pick up the moisture level gains that occur in a building either through perimeter walls on humid days outdoors or by occupants, open sinks, toilets, kitchens, etc., anything that adds moisture to a space. So, and again, the advantage of an outside air system is using heat recovery as a standard option in a DOAS 100% outside air unit. Let's look at underfloor air systems. What is an underfloor air system? It is an air distribution method that uses an enclosed pressurized floor plenum. HVAC supply air is delivered through diffusers mounted in the floor. Today's technology is very promising because plenum floors no longer need to be 16 inches plus to assume mechanical fan terminals in the floor plenum to service perimeter zones. We can actually remove those fan terminal units from that plenum. Ceiling spaces are open, free from overhead ductwork, and the possibility of looking at reduced floor-to-floor heights offers some very compelling architectural savings. So we're mechanically, and maybe in using an underfloor or using a plenum floor solution in a UFAD design might come across immediately more expensive. There are other architectural savings to be had that can bring about parity possibly in the overall first cost if a more holistic approach is adopted for doing the energy or doing the actual financial budgeting of these systems. Again, underfloor is very energy efficient. Systems being, or plenum is being designed to 0.05, 0.08 inches of plenum pressure, resulting in reduced fan horsepower, as well as, because airflow is at 65 degrees, we can actually increase economizer hours certainly in areas of dry geographical climate zones. The enclosed plenum pressure, again, results in thermal plumes. Wherever there's a heat source or surface temperature greater than the room set point, a thermoconvective plume results, drawing cool, conditioned air across the breathing zone, while that thermal plume will remove contaminant warm air to the upper levels of the space where it's exhausted from the room. And it's because of that thermal plume and its efficient removal of contaminants from the occupied zone, that ASHRAE has assigned a 1.2 ventilation effectiveness to this thermally stratified environments, including underfloor air systems. So when underfloor air systems are designed, because they are only being designed to the occupied zone within the zone. That is to say, the sensible heat load is only calculated for the occupied zone, or 6 feet above finished floors and 1 foot in from the walls. The upper 1/3 level of a conventional room height, you don't factor that sensible heat gain because the occupied zone doesn't see it. Now, the other side of the coin is that might think that, well, that means maybe reduced airflow is necessary. That's not necessarily the case, because a mixed air system, which is usually about 1 CFM per square foot to create a thoroughly mixed environment to meet space set point conditions, well, a displacement ventilation system or an underfloor system is bringing 65-degree air in. So the warmer air means that you have to increase the airflow to condition the occupied zone, which is about the same as bringing 55-degree air in to service the whole cubic volume of space in a mixed air system. When using underfloor air, one should be aware that if you have an east-west exposure and glazing, there's a radiant load that'll heat up the floor. And so you have to pay close attention that you're assuming the appropriate radiant load on that direct sunlight effect on those exposed areas with large areas of glazing. There are two air delivery solutions for underfloor air. There's a semi-turbulent design that injects air into the occupied zone about 5 foot into the zone and creates a semi-mixed air condition within the occupied zone. And then thermal stratification from an occupant removes that contaminated warm air to the upper level of a room. So a mixed air underfloor system supplies more air through each floor device to create a higher velocity discharge. There is also a displacement ventilation solution that uses more diffusers with lower airflow that actually spreads the air out along the floor to create a thermally stratified environment throughout the full height of the space. Now, ASHRAE 62.1 recognizes a 1.2 ventilation effectiveness for both the semi-turbulent design and the displacement ventilation. It really is up to the owner's needs, the budget or whatever, to decide on which way to go and what the overall project objective is. So a high velocity discharge semi-turbulent diffuser injects air at a high velocity to create a mixed air environment in the space. The amount of flow through these diffusers is dependent upon the plenum pressure. Airflow rates are dependent upon plenum pressure. And to give you an idea, hopefully I have better luck running this video, let's have a look at how that air in a semi-mixed condition is injected into the space. You can see the high velocity discharge profile of the air that stops at about 5 feet because it's creating a mixed air condition within the occupied zone. Then for displacement ventilation, less air is supplied through each diffuser. The same principles apply with regard to plenum pressure, so there's no advantage or disadvantage there. Plenum heights are the same. The difference is that the whole space from the floor to the ceiling is thermally stratified. One could argue, does it offer a level of better indoor air quality? Conceptually, possibly. I've not seen any papers or studies that made a comparative evaluation between semi-turbulent and displacement ventilation floor diffusers. So what's exciting about underfloor air is that it's a technology that continues to evolve. In the past, fan terminal units were required to condition perimeter zones, areas with high load swings such as conference rooms, and those terminals were of a certain height, about 14 inches, that often required floor plenum heights to be 16 inches or taller in a space. So a lot more room was required. Sometimes in very large open floor plenums, booster fans were required. And also other mechanical items were necessary, such as power transformers, power wiring, Cat5 control wiring for VAV applications, etc. New UFAD technology offers, however, it's completely different. No mechanical device is now required that requires floor access, moving floor terminals or floor tiles. Devices can be serviced directly from the floor side. You don't have to remove tiles. There's minimal wiring, Cat5 cabling due to wireless thermostats being available in the industry today. Minimum power wiring to do that. So this is pretty attractive now that the service of UFAD system equipment is no longer necessary by removing floor panels and getting under the floor to actually work on components. Perimeter heating is different. Instead of using fan terminal units, linear troughs are now provided along the perimeter with either electric or hydronic heating devices in them to wash the perimeter walls with warm air in heating mode or cool air in cooling mode. And this takes the place of the fan terminal unit that was used in the older technologies. So there are various architectural advantages. Less or no overhead ductwork, so the opportunity for reducing floor-to-floor heights occurs. You can actually showcase architectural features more effectively with an open ceiling. You can increase window sizes in the space, and all these systems are a modular design that can reduce the cost of remodel and churn within a building by moving around movable cubicle offices within large open environments. Passive radiant cooling and heating is another passive heat transfer mode that we can be applied into buildings. So passive heat transfer actually uses the electromagnetic spectrum as the heat transfer medium. By creating a thermal imbalance of surfaces locally within each zone, we can drive sensible heat loads in a space to a more dense heat transfer medium, such as water, and more efficiently remove that energy using pump horsepower versus fan horsepower that would otherwise be required. That can be achieved by actually cooling ceilings using chill water temperatures of 3 to 4 degrees above space dew point, or heating ceilings to provide a radiant heat effect. And my wife and I had the good fortune to enjoy some time in Scotland in September, and we stayed at an Airbnb that had a wall heater on it. It wasn't a convective radiant heater that we've seen in the old days. It was actually a radio bars along the wall. And she commented, which was always very good, how comfortable it was to have that radiant effect coming from a warm surface within that space. So just share with you an actual experience of that, certainly in a cooler climate. So heat transfer in a zone that is using the radiant effect requires less fan energy to move the energy from that space. There are different types of radiant devices that can be used. There are radiant panels. If you cool that radiant panel to 58 to 60 degrees, it'll absorb any of the energy present on any warmer surface and giving a cooling effect. And if any of you have had the opportunity to stand before maybe the mouth of a large cave where it's cooler, or maybe in front of a cooler, you feel cooler because the radiant energy that your body is given off is absorbed and relieved from the environment of your presence. So you have that cooling effect, which offers a thermal comfort component. So radiant panel technology can offer up to 25 to 30 BTUs per square foot of ceiling panel in cooling and up to 100 to 200 BTUs in heating. There is also a convective effect on radiant panels in cooling mode. The air adjacent to the panel surface is cooled via conduction, and that air will drop into the space normally. And so you do have convection occurring with these devices as well, offering some supplemental cooling effect. There are radiant sails, which are more effective in cooling because of the convective effect. These are continual these are louvered devices in the ceiling that allow air above the radiant sail to be cooled and through convection pass through the actual radiant sail, adding more heat transfer capacity in cooling mode of around 40 to 55 BTUs versus 20 to 30 with a radiant panel. A radiant panel system, however, can be a ceiling system. The manufacturer we represent could provide active, inactive panels within their ceiling systems, so you have a seamless integration so that you have tighter control and a better aesthetic effect, perhaps, in a panel if that's what the architect is looking for. Radiant sails do, however, offer a very dynamic linear quality in the open ceiling application, and you can see these devices can be customized to meet the aesthetic design desires of an architect in a building very effectively. Now, when you're designing to a radiant system, an engineer needs to pay attention to what is called the airside load fraction rate. So how do you design a radiant system? And that includes even for underfloor air systems. What you do is you define the minimum outside air requirements per each zone per ASHRAE standard 62.1. You see the find out what type of sensible cooling effect is present within the outside air being supplied to the space. And that defines how much supplemental sensible load needs to be addressed to maintain space temperature set points at thermostats. And then you look at the certified performance of a radiant panel or sail, see how much sensible cooling they offer at the available chill water temperatures supplied to them, and then see if the capacity meets or exceeds the sensible load to the space. If it does not, because of how the various sensible loads within a zone, then it may be necessary, depending on the available square footage available in a ceiling, to use low mass radiant devices to increase the outside air load fraction rate to pick up any supplemental sensible cooling requirements that might be necessary. In heating mode, that should not be a challenge, however. So any airside load fraction rate that is calculated to be below 1 represents that there's a fan energy savings because the sensible load is being effectively driven to the chill water loop that requires less pumping, that requires less horsepower due to pumping than fan energy horsepower that would otherwise be required. There's some ideas of some calculations roughly on airside load fraction rates of offices being at 15%, so they're ideal. Classrooms at an impressive 33%, they can make all the sense in the world, and even lobbies depending on their architectural design. So when designing radiant systems, it is important that you keep some design factors in mind. First of all, you have to design the outside air to meet all the ventilation factors. Minimum ventilation requirements per ASHRAE 62.1. The supply air of the 100% outside air unit needs to be appropriately supplied at a low enough dew point to absorb the humidity gain of that space. so that that space dew point will not exceed the chill water temperature serving the radiant devices. Otherwise, you'll have condensation. The challenge that we've had, in my experience, has been with chill beam systems and decoupled hydronic 100% outside air systems, has been inadequately designed OS supply air at dew points of 53 and 54 degrees. Is achieved at 55 degrees off a cooling coil. If you're using these systems, depending on your latent load in the space, you may want to look at 52 degrees, 50 degrees. Make sure your outside air is at a low enough dew point to absorb the moisture gains within that space to control relative humidity factors. So keep these design issues in mind. So when you're looking at a dedicated outside air unit serving a thermally stratified environment, look at what the supply air dew point condition is and make sure that it's adequate. Because buildings are continually being inundated by moisture. Again, going back to physics, high humidity state always sends moisture from a high humidity state to a drier state. It's called latent energy and the vapor pressure effect. Again, wherever there's an imbalance of energy, high energy states move to low energy states. Well, a high humidity state is a high energy state. It will always migrate to low. So your biggest challenge is certainly in Arizona during our monsoon months, humidity infiltration from the perimeter. We're outdoors. We're seeing now dew points in the mid 60s, low 70s. I've seen it this last summer monsoon in August. So humidity control is very important in appropriately designing passive radiant cooling and heating designs. So with these technologies available, we have 100% outside air systems, we have underfloor air systems, and we now have radiant technology available to us today. What if we take an integrated design approach to meet our current industry challenges? I've showed this slide before at a number of presentations, and so bear with me just to revisit it. But on March 6th of 2024, the Department of Energy issued the determination that ASHRAE Standard 90.1 2022 has been determined to be the energy performance baseline buildings have to meet, and municipalities have up to 2 years to incorporate its language into their codes. Now, we know how that goes. It'll actually be 5, 8, maybe even 10 years in some areas where this is adopted. But what is encouraging, we do know that the city of Scottsdale here in Maricopa County and the city of Chandler has adopted the IECC 2021 code that has acknowledged 90.1 2019 as the energy performance baseline. So we do see our codes, even in a very conservative area of Maricopa County and Arizona, of various municipalities adopting these more stringent codes. ASHRAE has taken an aggressive stance on decarbonization. In fact, they have their task force on decarbonization. And it goes on to say in their decarbonization paper that ASHRAE's role is to be a leading source of information for HVAC&R systems and building performance that serve as resources for building decarbonization, including writing and updating energy standards, building performance standards to reduce energy consumption, create high performance building standards, not only for energy efficiency, but also for indoor environmental quality, where we spend 90% of our lives indoors. Provide a consistent method of testing, expressing and comparing the energy performance of buildings. And we see that in expanded commissioning language in ASHRAE Standard 90.1 2022. ASHRAE's building decarbonization paper goes on to say that worldwide concern for changes in global climate has escalated as scientific evidence has become more definitive linking increased concentrations of atmospheric greenhouse gases with global warming. And I was surprised that it used global warming and not climate change. Personally, I think it's probably a more accurate term. Building decarbonization addresses the following involving design, construction, operation of buildings. It goes on to say that reducing the carbon balance of the building and its operations, reduced operationally generated greenhouse gas emissions, reduce energy demand, also reduce embodied carbon and that is associated with the manufacturing of mechanical equipment. And ASHRAE's position document on building decarbonization has this very aggressive statement that by 2030, to at least half building 2015 greenhouse gas emissions and to be net zero by 2050. Well, to meet that challenge, mechanical systems are going to have to be reevaluated, more efficient equipment needs to be designed, and more innovative approaches to HVAC will have to be adopted. So one approach, of course, is to rethink how we do HVAC, take advantage of passive systems that offer passive heat transfer within the zones of a building. And one of those solutions, of course, is using radiant heating and cooling systems that uses the heat transfer modes of conduction, evaporation, convection, and radiation in the system to achieve greater efficiency, exploit the added economizer hours or free cooling available with these systems, provide better indoor air quality to meet the indoor air quality and indoor environmental quality standards, and to create better thermal comfort. Also to look at 100% outside air passive radiant systems because of outside air delivery solutions being more efficient for reasons expressed. Variable air volume control or personal manual control is available at each floor device. Superior indoor air quality, low maintenance, reduced mechanical footprints, and basically an integrated system for optimized performance by applying the principles of convection and radiation locally in each zone, offering a compelling design concept for creating healthier, more efficient. So 100% outside air, underfloor, radiant cooling and heating systems is a design concept that is perfectly doable today. Each system has been proven and vetted out to be effective. And if we bring them together, they can offer arguably one of the most efficient systems in the industry today that optimize indoor air quality. Well, that is it for today's presentation. And I just want to personally take a moment to say thank you. Thank all of you for participating in the webinar Wednesday sessions. We wish you all a very happy Thanksgiving and a safe and blessed holiday season. We hope to see you in 2025. Thank you.
All right. Thank you, Dan. We don't have any questions in the chat, but if anybody does have any questions, feel free to unmute yourself or pop them in the chat. Brian did enjoy jamming out with you, though, Dan.
Thank you, Brian.
You had me panicked for a second. I was trying to figure out who I needed to mute. That's why I asked if it was coming from you. Yeah, I'll give it a little bit to see if anybody has any questions.
Sure.
Hello?
Oh, yep, go ahead.
I have a question.
Yes.
All right. With respect to the underfloor system, let's say that the area is a heavy trafficked area and it's a carpeted area, and foot traffic causes, I don't know, pathogens or whatever that's been on people's feet and things like that, the shoes from outdoors, allergens, things like that. Is it picked up in the airstream? Has any research been done on whether there's any pathogens that do end up in the airstream from the floor? It's always been a concern.
And you know what? That's an understandable concern. I can only speak to it as I'm not aware of any study. I think it could be dependent on which underfloor air delivery solution you choose, whether it is the high velocity discharge solution or whether or not it's the displacement ventilation low velocity discharge solution.
Mhm.
Particles are of a greater mass than air, so any particle, and arguably germicidal pathogen, would have a tendency to fall out of the air quicker than really air in itself traveling. So I think it would be difficult to imagine in a displacement ventilation UFAD system from that actually occurring. In a semi-turbulent design, potentially there could be some cross-contamination within the occupied zone due to the mixing, especially with aerosolized pathogens. But I'm speaking conceptually. I'm not aware of any study that's been written to that effect.
I worked on an underfloor system for one of the major buildings here in New York. And
Ah,
when I did look at it back then, it was always a concern. And the thought process was sealing the floor properly and then spacing out the underfloor diffusers in a certain way. But the concern was always in a carpet. When you hit a carpet, sometimes, the vacuum doesn't pick up everything. So there's
yeah.
always dust and things like that. So as you put as there are footsteps hit the ground, doesn't it always cause like a micro dust cloud behind every footstep, theoretically? So it was always a thought that can it be picked up in the airstream and actually move around?
Well, that's a good observation, but let's look at it from another way. Let's look at an all mixed air system. ASHRAE Standard 55 says that terminal velocity of overhead air distribution has to be at 50 feet per minute at the occupied zone, or 5 to 6 feet above the floor. So you have mixed air velocity coming down to the floor anyway. Is it 20 feet per minute, 30 feet per minute? So you could actually argue that with the walking, a mixed air system is doing its job by uniformly mixing that contaminant
Mhm.
throughout the cubic volume of space. Whereas the discharge velocity, certainly from a displacement ventilation UFAD system, is less. And by the way, the air current is to be laterally off the diffuser along the floor, so it doesn't encourage that to occur. Now, with regard to thermal plumes, you might hear it with a UFAD displacement or any displacement ventilation system that an occupant thermal plume is roughly about 50 feet per minute if somebody's body temperature is hopefully 98 degrees in a room set at 75 degrees. There's a 23-degree temperature differential. You have a heat source. But it's not 50 feet per minute across the occupant. Where there's low thermal mass at the ankles and feet, you might have a velocity of 2 to 5 feet per minute. It's not until that air reaches the thorax where we have high mass thermal energy present
Uh-huh.
that all of a sudden we see an acceleration of that thermal plume that averages out to 50 feet across the body, but it could actually be 60 to 70 feet per minute by the time it crosses the breathing zone. So with regard to the picking up of contaminant, which is, you raise a very compelling question, by kicking up dust in the carpet, it could happen, but its chance of being induced into that low velocity thermal plume at the ankles is less likely to occur.
Honestly, the biggest concern was pollen, really, because
Oh,
if there's pollen in the air and pollen falls to the ground, then pollen gets dusted up again. It'll affect people who are susceptible to allergies from that. And that was the curiosity I've always had with that. Again, from having seen a floor underfloor system, one of the first ones here in New York City. So
that's
that
that's
was my thought.
that's an excellent question. But remember, even in a mixed air system on a carpet, that dust is being kicked up.
Mhm. Okay, I see what you're saying. Okay.
Yeah, and
Well,
then it's being mixed into the space for the lighter particles.
mhm. All righty. Well, thank you very much for that insight.
Oh, my pleasure. Thank you for the question.
All right. Does anybody have any other questions? Okay. Well, hearing none, I think we can wrap this up, Dan. As Dan mentioned, thank you all for joining us for our last one for the year. Have a safe and happy holiday season and look for our new schedule for 2025 and the first webinar Wednesday to kick off in February. As always, Dan, you did a fantastic job. Thank you so
Um,
much for all the knowledge.
Always a pleasure. This is fun. So thank you all for joining us and have a very happy Thanksgiving.
All right, thank you.
Bye bye.
Thank you.